Okay, here we are. This is one of our last talks for the day. We only have a couple of things remaining, and you're all in for a treat. So, Mike has already said something that I share, a sentiment I share, which is Nick is one of my favorite conference speakers of all time. Nick has an incredible ability at storytelling. He has an incredible ability at walking us all as audience members through a journey. So, you are all in for a treat if you're not familiar with Nick or Nickolas Means. So, a couple of quick things though before we dive into Nick. So, if you didn't know, there is a head-to-head competition going on, an unannounced competition between the 5Kers, the run, walk, roll 5Kers, and the 30-minute exercisers. There is 25Kers who have logged it and 21 30-minuters that have logged it. So if you have not yet put in your 30 minutes, or if you've already done a 5K or 30 minutes of exercise and just haven't recorded it into the Airtable form, now's the time. I mean, this is an unofficial competition, but heck, why not? Here, we're so close. The last thing I want to throw out there is your 60-second Ruby story. There is a channel called My 60-Second Ruby Story. And I would love if you took a moment to tell us what is your 60-second story that got you into this community. It's an incredibly vibrant, incredibly loving, and incredibly caring community. And I want to encourage all of you who have a story of any kind. What got you here? What was that inciting blog post, video, or person that brought you into all of this? So if you would, head on over there, let us know. Okay, well, without further ado, I want to introduce Nick Means and bring him onto the stage. Almost. We're almost there.
There we go. It's coming.
Yes, it is. Well, hello, Nick, my friend.
Hello.
I am very excited to introduce you. I really do mean it. You are one of my very favorite speakers, so I'm excited to share you with the world, Nick. That's what we're going to be doing. I'm sharing you with the world.
I'm excited to be here. Before I go, I have a question for you. If I've done 2 5Ks and 30 minutes of exercise, should I log it all?
I don't know. I didn't create the rules. I only created the rules, Nick.
Okay.
Who knows? But, why not? All right, very good. Well, without further ado, Nick, the floor is yours, or the stage is yours.
Thank you so much for that intro, Adam. It is such a privilege to be back with my friends in the Ruby community. I had to miss RubyConf and RailsConf last year, and that was such a bummer. So I am so happy to be back. Now, some of you may remember seeing a different talk on the schedule for me. I had to make a change last minute, unfortunately. We lost our sweet 17-year-old dog last Friday, and I just didn't have the emotional capacity to finish turning my giant pile of notes into a finished talk. The good news is that I have another talk that I wrote recently that actually gets at a lot of the same themes. So I hope you enjoy it. It's no secret at this point that I like planes, but today is a special day for me because I get to tell you the story of one of my very favorite planes, Concorde. Now, to tell the story well, I have to start several decades before anyone had even started thinking about Concorde. Because to understand what Concorde achieved, we have to start by understanding supersonic flight. And that means starting with the Bell X-1. This plane, piloted by Chuck Yeager and powered by 4 rocket motors, was the first aircraft to fly faster than the speed of sound in level flight, flying at a brisk Mach 1.06, about 600 miles an hour, on October 14th, 1947. Breaking the sound barrier was a huge achievement. Until Yeager did it and came back home safely, it was a widely held belief that doing so would be unsurvivable. And this was for good reason, because so many previous attempts to fly close to the speed of sound had indeed proven fatal. Pilots exceeding Mach 0.7 entering the transonic zone often encountered strange problems with their planes. The controls in the Mitsubishi Zero would freeze because of the aerodynamic loads on the wings. The controls on the Supermarine Spitfire would reverse unpredictably somewhere between Mach 0.7 and Mach 0.9 as the wings flexed, and the plane would do the opposite of what the pilot commanded it to do. And the de Havilland DH-108 Swallow, flown in progressively faster dives in a program attempting to fly faster than the speed of sound, experienced severe buffeting just above Mach 0.9, causing it to break apart. There's a reason it came to be called the sound barrier. So what exactly happens to a plane as it gets close to the speed of sound? To understand that, we need to talk about how a wing works in the first place. Bernoulli's principle says that in any fluid, including air, an increase in speed results in a decrease in pressure. Airplane wings are designed to take advantage of this. The curve of the top of an airplane wing slightly increases the distance air has to travel to get over the top versus below, meaning it has to move faster. And Bernoulli's principle tells us that faster speed means that the pressure on top of the wing is lower, and that lower pressure is what gives the wing lift. That all changes as the plane approaches the speed of sound. At speeds below Mach 0.7, air flows around the wing smoothly. As the air gets faster, though, it starts to move too fast for the air to move out of the way before it gets there. So the air at the leading edge of the wing starts to compress, causing tremendous drag. And then once the air is past the leading edge of the wing, it rapidly decompresses, causing a shock wave that disrupts the flow of air over the wing. This means the wing struggles to efficiently generate lift. This drag and reduction in lift is why it seemed like there was a barrier at Mach 1. It was literally like hitting a wall. The X1 was able to break Mach 1.0 because it was basically a flying bullet. The fuselage was actually modeled after a 50 caliber machine gun bullet, a shape known to be stable at supersonic speeds. It had short, thin wings, which minimized the drag and shockwave they created, but they also didn't generate very much lift. The meaningful payload of the X1 was fuel plus a single person. People the world over were speculating at our supersonic future and the idea of jaunting from New York to London after hearing how fast the Bell X1 could go, but we were a long way from being able to do it. The next big breakthrough in flying supersonically was the Fairey Delta II, first flying in 1954 and becoming the first plane to exceed 1,000 miles per hour in level flight. The FD2 introduced the concept of a delta wing, which had a couple of significant benefits. First, on a traditional design, the elevators, the control surfaces controlling the pitch up and down of the plane, are on the tailplane. Because the wing on a delta design is so elongated, it doesn't need a tailplane at all. Instead, using elevons, a combination of elevators and ailerons, on the trailing edge of the wing to control both pitch and roll. Second, the delta design has a huge advantage in how much surface area it presents to the air that it's moving through. Both designs have roughly the same wing surface area, but because the wings are so deeply swept and there's no tailplane, the delta design has a much smaller surface area facing forward for compression to cause drag at supersonic speeds. The delta design does have one huge disadvantage, though. It's incredibly inefficient at subsonic speeds. In order to produce enough lift to get off the ground and climb, it has to fly at a very steep angle of attack, and that takes a lot of fuel. The FD2 proved the superiority of the delta wing for high-speed flying, but the inefficiency of the wing at low speeds meant that an airliner-sized delta wing plane would have to carry so much fuel, it wouldn't have enough useful load left to carry passengers. It was a step in the right direction, but it wasn't enough. The next step followed quickly. Early in 1955, Drs. Dietrich Kuchelmann and Johanna Weber, working together at the Royal Aircraft Establishment, published a series of papers detailing a concept they called the slender delta wing. Now, it was already known that any delta wing flying at low speed and a reasonably high angle of attack would create a vortex over the wing running along each side of the fuselage. Now, normally you want to reduce vortices and other kinds of turbulent airflow over a wing. But in this case, Kuchelmann and Weber theorized that these vortices might be doing an important job, speeding up airflow over the top of the wing. And according to Bernoulli's principle, faster air is lower pressure air. So these vortices were actually generating lift. But Kuchelmann and Weber went a step further. Their studies indicated that the more swept a wing was, meaning the smaller the angle between the fuselage and the leading edge of the wing, the more pronounced this vortex effect was. And the longer the wing, the more surface area this vortex had to act on, increasing the lift it was able to generate. That meant that a slender, long delta should be able to generate more lift at low speeds than a standard delta. And so RAE decided to test it. They built a prototype. The plane they built, the Handley Page HP-115, is nothing more than a test bed for the slender delta concept. They only built one, and it served no other purpose. But it worked perfectly. You can see the plane here flying at the necessary high angle of attack, and the smoke shows the vortex that's formed over the wing. You can see it swirling as it comes off the trailing edge of the wing there. Given the extra lift generated by the vortices, this plane was safely controllable as slow as 70 miles an hour, which is a 300% improvement over previous delta wing planes. Now, this was enough for the UK government to fund study contracts to 2 British aircraft manufacturers to attempt to design a slender delta supersonic transport. And the Brits weren't the only ones working on an SST. Across the English Channel, the French had launched their first successful supersonic plane as well, the Dassault Supermisteret fighter bomber. The French knew the British had begun an SST project and were eager to not get left behind, so they began pursuing an SST in earnest. The French government awarded grants to 3 manufacturers, Nord Aviation, Sud Aviation, and Dassault, to begin work on SST concepts for a design competition. And across the Atlantic, late in 1956, the Americans had just flown the Mach 2 capable Convair B-58, the first supersonic bomber. Wasn't a great design, it was difficult to control and had a very narrow flight envelope, but it could carry a significant load at twice the speed of sound. American aircraft manufacturers were trying to parlay this expertise of bearing load quickly into something that could carry passengers, but the US government just wasn't interested, so funding was sparse. And in the USSR, their focus on the space race wouldn't prevent them from getting in on supersonic flight as well. They already had a couple of supersonic fighters in the famous MiG series, including this MiG-21. In 1958, just after the launch of Sputnik, they debuted this plane, the Yakolev Yak-28. It's not a big plane, but it is a bomber. Where the MiGs are basically a cockpit strapped to an engine, this plane has significant load capacity. The Soviets also knew through their extensive espionage network that the UK and France had both begun working on a supersonic passenger plane. And so they took what they knew and they set to work. And so at the end of the decade, in 1959, there were 4 nations in the race to fly a plane full of passengers faster than the speed of sound. The UK, France, the US, and the USSR. All of them just getting started. The French would be the first to tip their hand, announcing this plane at the 1961 Paris Air Show, the center of the commercial aviation world. Sud Aviation's Super Caravelle design had won the competition among French manufacturers. It was intended to fly 75 passengers at Mach 1.2 on mid-range overland routes within Europe. The French announcement at the Paris Air Show kicked off a few key developments in the SST race. First, not to be outdone by the French, the Soviet government announced their SST project, the Tupolev Tu-144, early in 1962. This publicly confirmed to the UK, US, and France that the Soviets were indeed working on an SST. Second, despite the lack of government funding, NASA had been funding SST research and development in the US via the SCAT prototypes in the name of General Aeronautical Research. The inauguration of John F. Kennedy in 1961 changed the US government position on an SST almost overnight, and the US handed research contracts to 4 major US aircraft manufacturers to develop the NASA prototypes into planes, with design competition entries due 3 years later in 1964. And finally, the French announcement presented a solution to a problem the British were very eager to solve. Bristol Aircraft had won the UK SST design competition with this design, the Bristol Type 223. It was to seat 90 people and fly Mach 2.2. The problem was that BOAC, the British Overseas Airways Corporation, the predecessor of British Airways, said that while it would be delighted to buy and operate SSTs if they made economic sense, they would not be willing to bear any of the cost of development. That meant that the British government would need to fund the project if it were to happen. Given the estimated cost of development and the unknowns involved, the British government needed a partner to bear the risk. The Super Caravelle design that the French had announced was so similar to the Bristol 223 that they made perfect sense together. The French had found themselves in the same dilemma as the British. They had a great design, but they couldn't afford to take on the risk to develop it. And so the transport ministers of the British and French governments instructed BAC and Sud Aviation to get together and work out a combined design. A short treaty signed in late 1962 cemented the country's relationship and gave the project its name, Concorde, meaning peace and unity in both English and French. While the Americans were busy with their design competition, things started moving very quickly in Europe, and the design for Concorde was finalized. Construction of 2 prototypes began in February of 1965, one at the Sud Aviation factory in Toulouse and the other at the BAC factory in Filton. The next year in the US, Boeing's entry, the 2707, was named the winner of the design competition. This is an early full-scale mock-up of the design. It was to hold 277 passengers, and it was designed to fly Mach 2.7. One of the key components of the design was a swing wing mechanism, which you can see here. The wing would swing forward for efficiency in low-speed flight and swing back into a delta configuration to minimize drag at supersonic speeds. Boeing expected to start on a prototype in early 1967, aiming for a first flight in 1970. They knew they were behind Concorde, so if they were going to be late bringing their SST to market, they at least wanted to bring a better SST, one that carried more passengers and went faster. Later that year, on December 11, 1967, the first Concorde prototype was rolled out of the hangar at Sud Aviation's factory in Toulouse, France, in a ceremony attended by the media and dignitaries from both countries. Now, the wings are obviously the biggest innovation in the Concorde, but let's talk about a few of the other things that make this design so special. First, if you know anything about Concorde besides that it was fast, you probably know about its droop nose. But why was that necessary? Well, it all goes back to the wing shape. Despite the vortex optimization, Concorde still has to fly at a significant angle of attack to generate lift while flying slow, including when coming in for a landing. That steep angle would mean that the pilots couldn't see the runway for the nose of the plane, So they simply folded the nose with its streamlined windscreen down out of the way, revealing the primary windscreen behind it. The double windscreen configuration had the side effect of reducing the need for cooling in the cockpit by keeping some of the Mach 2.0 kinetic heating from reaching it. But the windscreen wasn't the only place kinetic heating was a concern. It affected the entire plane. What is kinetic heating? Well, as you compress air, it gets warm. If you've ever filled up car tires and noticed the hose getting warm as you did it, this is what you're experiencing. There's also significant friction against the leading edges of the plane, also generating heat. What this means is that when Concorde is going Mach 2, it could be over 240 degrees Fahrenheit at the tip of its nose, with slightly lower temperatures elsewhere. So the designers of Concorde did a few specific things to cope with this heat. First, they very deliberately chose just over Mach 2.0 for Concorde's target cruise speed as they were designing the plane. And the reason for that was that if Concorde went any faster than Mach 2.2, they couldn't build it out of aluminum. Aluminum is fantastic for building planes because it's strong and light, but it begins to lose its structural integrity at around 266 degrees Fahrenheit. Going any faster than Mach 2.2, like the Mach 2.7 the Americans were designing for, meant that they'd have to work with an exotic metal like titanium, and it would significantly extend their timeline. Mach 2.0 was a very pragmatic choice. But even at Mach 2.0, Concorde would still accumulate a lot of heat. They still needed to keep their passengers comfortable and keep things like hydraulic fluid and oil from overheating. They came up with a very clever answer for that. They used their fuel as a heat sink just before they burned it. There were heat exchangers in the engine feed tanks that took heat from the air conditioning packs, the hydraulic system, and the oil system and heated up the fuel just before it was burned. All that excess heat went right out the engine exhaust, keeping the passengers nice and cool and the plane working beautifully. They also used fuel, interestingly, to keep the plane trimmed. One of the effects of flying supersonically is that because of the change in forces exerted on the wings by pressurized air and shock waves, the wing's center of lift moves further back as the plane speeds up. This pushes the back of the plane up and the nose of the plane down. Now, conventional wisdom would say to use the elevons to account for this, applying a slight nose-up force, but using elevons would add drag, reducing Concorde's range. So instead, Concorde is trimmed by moving fuel around. As the plane speeds up, fuel is gradually pumped from these tanks in the front to this tank in the back of the plane. The added ballast counteracts the shift in the wing center of lift by moving the plane's center of gravity rearward as well, helping it fly level without having to pay any drag or range penalties. But Concorde's biggest innovation was its ability to supercruise. Most supersonic aircraft that had been built to this point could only fly supersonically for a few minutes. And the reason for this is that they had to use afterburners to achieve supersonic speeds. The orange glow of afterburners is what many of us think of when we think of jet engines, but most jet engines don't work this way. You'll never see this happening on a commercial plane you fly today. What an afterburner actually is fuel injected into a jet engine's exhaust stream and lit. Now, this happens past the engine itself. The combustion adds significant heat to the exhaust gases, and because gases expand as they're heated, this forces the exhaust out of the jet nozzles faster, adding significant propulsion. But it's horribly inefficient, burning a tremendous amount of fuel in the process and generating a ton of noise. This is why most planes that rely on afterburner for supersonic speed can only fly supersonically for a few minutes at a time. They'd run out of fuel. And Concorde had afterburners as well, but it only needed them for a couple of specific phases of flight. They were used for takeoff to give the inefficient at low speeds delta wing the extra oomph needed to get off the ground, and they were used again to pass through the sound barrier, giving the plane the extra boost needed to overcome the initial resistance at Mach 1.0. Above Mach 1.5 or so, though, they turned the afterburners off, and the engine intake ramps did all the work. The doors you see at the front of the intakes, where danger is written in red, swing down to reduce the size of the intake opening. This generates significant compression. Jet engines work on compression, taking a huge scoop of air in the front and compressing it down and sending a narrower, much faster stream of air out the back, pushing the plane along. If you've ever put your finger over the end of a water hose to spray water, it's the same concept. These ramps generate significant compression when the plane is flying supersonically, reducing the work the engine itself needs to do and reducing the amount of fuel it uses. In fact, Concorde was at its most efficient when flying Mach 2.0, traveling far further per gallon of fuel than at any other phase of flight. Supercruise meant that Concorde had the longest supersonic range of any plane built to that point. It could fly from New York to London in 3.5 hours, about twice as fast as a conventional jetliner, even today. But at this point, all this innovation was still just theoretical. Concorde still hadn't flown. The rollout ceremony celebrated completion of the first prototype, but there was still a year of ground testing to do before Concorde's first flight, planned for early 1969. You may have noticed that we haven't been talking much about the Soviet effort. The reason for that is that the Soviet Iron Curtain was very effective at keeping things secret until they were ready to reveal them. So it was a big shock to the world when on December 31st, 1968, news footage emerged from the Soviet Union of the first flight of the Tupolev Tu-144. Much to the world's surprise, they had beaten Concorde off the ground. Not by much, though. Concorde wasn't far behind, taking to the skies for the first time a few months later on March 2nd, 1969. It would be a short flight, around 30 minutes, at 10,000 feet and 300 miles an hour. Captain Andrei Tarkat never even raised the landing gear, keeping things configured as simply as possible. The plane flew beautifully, with Tarkat declaring afterwards that it was even easier to fly than he expected, much better than the simulator. In America, things weren't going well. Late in 1968, the American team had finally come to the realization that the 2707 was an unworkable design. The weight of the hinge mechanism for the swing wing proved to be an insurmountable obstacle. One Boeing engineer quipped that if they wanted to cross the Atlantic, they'd need to decide between the hinge and the passengers, because the plane couldn't carry both. So that's just what they did. They pivoted to a new design with a fixed double delta wing. It looked a lot like an overgrown Concorde with a tailplane. At this point, though, they were way behind. Their competitors had already both flown, and they were starting over almost from scratch. The Americans were later than they realized. The Tupolev Tu-144 would go supersonic for the first time on June 5th, 1969, again beating Concorde to a critical milestone. Concorde would quickly follow, though, going supersonic on the 1st of October, 1969. A couple years later, 1971 brought about the end of the road for the U.S. SST project. Congress threw in the towel and eliminated government funding for the project. Boeing had already spent more than the entire Concorde program would spend, and all they had to show for it was this full-size wooden mock-up. 5 years later, Concorde had completed all of its required tests and trials and had received its certificate of airworthiness from European regulators. It could enter service, beating the Tu-144 to the milestone that counted the most. And so the first Concorde was handed over to British Airways on January 15, 1976. A week later, and takeoffs coordinated to the second from London and Paris, Concorde entered commercial service. The British Airways flight flew from London to Bahrain, and the Air France flight from Paris to Rio de Janeiro. Why those destinations? Because the U.S. Congress, in a move largely considered protectionistic, had banned Concorde in U.S. airspace for 6 months. 6 months later, on May 24, 1976, the ban would expire, and BA and Air France celebrated with coordinated landings about 10 minutes apart at Washington Dulles Airport. Why not New York? Well, after the congressional ban expired, the Port Authority of New York and New Jersey banned Concorde based on noise concerns. It wasn't until October 22, 1977, 17 months later, that the U.S. Supreme Court declared the Port Authority had overstepped its authority and Concorde was finally able to land at JFK, initiating the iconic London and Paris to New York route that it's best known for. The Tu-144 would finally enter passenger service on November 1st, 1977, nearly 2 years after Concorde. But by all accounts, it wasn't a very comfortable experience. Cabin noise was measured at 95 decibels, about as loud as a lawnmower when you're pushing it. Passengers seated next to each other could only talk to each other by yelling. It also had an incredibly high failure rate, and Aeroflot only flew it because the Soviet government told them they had to. When they had a flight, they would often prepare 4 Tu-144s in hopes that one of them would actually be able to complete the scheduled service. The Tu-144 made only 55 passenger flights in all before it was withdrawn from service. So what was it that made Concorde successful? Why did the Anglo-French Consortium succeed in delivering a plane where the Americans and Soviets didn't? Or at least I thought that's what this talk was going to be about when I proposed it. But the answer to that question is pretty simple. Compared to the American effort, the Concorde team made much more pragmatic choices. The Boeing design was much more complicated and needed to be built out of more complicated materials because of its higher speed. This overreach was its downfall, and the project was canceled. The application of software here is pretty obvious. The Soviet comparison is a little more interesting, but the thing that did it in was partial understanding. You've probably noticed the similarity of this design to Concorde, and this is for good reason. Significant portions of the Tu-144 design were derived from Concorde by way of the KGB. But they didn't apply all of the concepts exactly right. They didn't have a full understanding. The wing shape was similar, but the Tupolev was missing some of the 3D sculpting that makes Concorde's wing so effective at producing vortex. meaning the Tu-144 needed to be moving faster to take off and had to come in much faster to land. The Tu-144 positioned its engines much like Concorde and even used some of the same technologies internally, but it couldn't supercruise, limiting its range significantly. It didn't have the range to cross any oceans. The lesson here is to be careful what you and your team adopt from the practices and product decisions of others. If you don't deeply understand the things you're adopting, you'll likely not get the results you're seeking from them. And those are both important lessons. But as I got deeper into writing this talk, I realized that those lessons were pretty surface, and there was a much more interesting question here for us to ask. Was Concorde actually successful? Well, let's look at some numbers. The estimated development cost for Concorde was 70 million pounds, about $168 million at historic exchange rates. The actual development cost for Concorde came in at 1.134 billion with a B pounds, around $2.7 billion, a 1,600% cost overrun. That's about $20 billion today. That cost was paid by the British and French governments. Next, let's talk about sales. At its peak, Concorde had more than 100 outstanding options, essentially reservations from airlines for delivery slots. British Overseas, Air France, and Pan Am were to be the launch customers with 6 Concordes each. In the end, though, only 14 Concordes ever went into service, 7 each for British Airways and Air France. And there were a couple reasons for that. One was fuel economy. Concorde could fly a passenger 17 miles on a gallon of fuel. Compare that to the Boeing 707 at 33 passenger miles per gallon. Concorde is about half as efficient, but that was an acceptable trade-off given how much faster it could cross the Atlantic. But then came the Boeing 747-400 and its new turbofan engines, cranking out 73 passenger miles per gallon. Concorde's engines were so inefficient that it would burn 2 tons of fuel, about 2% of its full fuel load, just taxiing out to the runway before it ever took off. Another problem was sonic booms. Remember the shock wave that's produced by the compression and then decompression of air in front of the plane? That shock wave goes all the way to the ground and creates a sonic boom, the same way lightning creates thunder, only much more concentrated. And it's not just one boom when the plane crosses the sound barrier, it's continuous under the flight path. If a supersonic plane flies over you, you'll hear a boom. In spring of 1964, the FAA conducted an experiment over Oklahoma City, Oklahoma called Project Bongo. It's one of my favorite project names ever. They subjected the citizens of OKC to sonic booms, 8 per day starting at 7 a.m., to see how people reacted. The test lasted for 6 months, 1,253 sonic booms in all. Over the first 14 weeks of testing alone, 147 windows were broken in Oklahoma City's 2 tallest buildings, and the FAA received nearly 10,000 complaints. The conclusion was that regular supersonic flight over land was a complete non-starter. In fact, it was made illegal in the US in 1973, largely as a result of these tests. Concorde would be restricted to overwater routes, and Concorde's range meant that the London and Paris to New York route was really the only natural fit for it. Only British Airways and Air France followed through on their commitments to buy Concorde. So, was Concorde successful? Massive cost overruns, terrible fuel economy, almost non-existent sales? Seems like a clear no. But if Concorde was such a failure, why do we have pictures like this? That's a British Airways Concorde flying in formation with the Royal Air Force Red Arrows, the UK's version of the Blue Angels, at the Royal International Air Tattoo in 1985. Or this, a 1986 photo of an Air France Concorde leading the Patrouille de France, the French Air Force demonstration team at La Ferté Air Show. Or this 2002 photo of a British Airways Concorde leading the Red Arrows past Westminster Abbey as part of the Queen's Golden Jubilee celebration, just a year before the Concorde fleet retired. Or this photo, from last year's edition of the Royal International Air Tattoo, of the Red Arrows and the Patrouille de France flying together in Concorde formation, 16 years after Concorde's last commercial flight. And the list goes on. If Concorde was such a failure, why are the UK and France so proud of it? Turns out that this is a very nuanced question. It always is. That last question got real in a hurry. You probably had a pretty visceral reaction to it when it popped on screen. So let's go back to something a little more comfortable. Let's go back to our first question. Because it turns out the way that we answer this question is the same way we should answer that really hard question about ourselves. Daniel Kahneman wrote a fantastic book about understanding how our brains work called Thinking Fast and Slow. It's well worth your time to read if you haven't. There's a couple of concepts he introduces that will be helpful here. The first is the law of least effort. The law says that when we use our brains, we tend to use the minimum amount of energy possible for each task. In other words, our brains are lazy and they're constantly looking for shortcuts. And one of the shortcuts our brains use all the time, also discussed in the book, is the availability heuristic. And this is a cognitive bias that causes us to rely on and overvalue the information that's easiest for us to recall. And a big chunk of what's easiest for us to recall is the stuff that we've heard the most recently. These two effects together are why, after I spent 25 minutes sharing the amazing story of Concorde and all the innovation it represents, it only took me 6 slides to get your brain to flip and declare Concorde a failure. We do this all the time. So what happens when we slow down, pull our brains out of shortcut mode, and actually think about Concorde? First, we might consider the perspective of the folks at Aerospatiale and BAC who designed and built Concorde. They were given the task of building a plane that could carry 100 passengers across the Atlantic faster than the speed of sound. And they came up with a machine that was purpose-built to do exactly that. A plane that was beautiful not because they wanted it to be, but because it had to be to fly that far that fast. A plane that was so innovative that it felt plucked from the future, even when it was 25 years old and began being forced into early retirement. The designers and builders of Concorde must have considered it very successful indeed. What about the British and French governments that footed the £1.1 billion development cost? It had to have stung that the plane didn't sell any better than it did, right? Well, let's consider what the governments of Britain and France were actually paying for. It wasn't profit. Certainly they were hoping to see that money paid back, but they weren't trying to make money. What they were actually paying for was this, a point of national pride. Multiple commentators have referred to Concorde as Europe's moon landing, its biggest technological triumph. It was also a demonstration of aviation capability. British and French entrance into the commercial aviation market hadn't sold widely for a variety of reasons, and the American Boeing 707 was dominating the skies everywhere. The governments of the two countries saw a supersonic transport as their path back to relevancy in the commercial aviation market. And it took a while, definitely longer than they expected, but they got what they paid for. Airbus is a direct descendant of the Anglo-French consortium that built Concorde. And this plane in particular, the Airbus A320, is the second most widely produced commercial aircraft family in history, behind only the Boeing 737 and probably not for much longer. So back to our question, was Concorde successful? If we focus on the 60s and 70s, the year Concorde was being produced, and we look at the short-term facts, we can make a pretty strong case that it wasn't, that it was way behind schedule, that it lost a ton of money. But when we look at Concorde's full impact, the prestige it brought to the UK and France, the foundational role it served in the European commercial aviation industry, the sheer amount of economic activity that descended from it, it's hard to see anything but incredible success. So we've sorted out the first one, but what about the rest of these? Well, the same rules apply. Though we often don't have the luxury of looking back on 40 years of history the way that we can with Concorde, we do usually have more information than we take advantage of. We often ask questions like these in the heat of the moment, sometimes in the middle of a crisis, and because of the shortcuts our brains take, we answer them through the myopic lens of the right now. That's what makes "Am I successful?" such a scary question, why we have such a visceral reaction to it, but we unconsciously answer it all the time. This project is so hard. It's way beyond my ability. I'm such a failure. This incident is all my fault. I can't believe I did that. I'm such a terrible engineer. I'm so far behind. I'm letting everyone down. I'm a horrible manager. I've said all of those things to myself at some point in my career, some of them pretty recently, and I'm sure you have as well. But when we do that, we take a short-term evaluation that's likely not even true or fair, and we extrapolate it to the entirety of our being. We tear ourselves down because our brains are lazy by nature and take every shortcut they can in answering the question. And so here's my challenge to you. Zoom out. Think about the impact you want to have in life, the things you actually care deeply about. Whether you respond to that email today or deliver that project this quarter may be important, but it's likely not enduring. Some of the relationships you build along the way absolutely will be. Your brain will stay in shortcut mode if you let it, just going with the flow of events around you. So you have to choose to live intentionally. You have to choose to zoom out, to remember that there's far more to life than what you're feeling right this moment. So when your brain or some jerk speaker stops you in your tracks with this question, take a breath. Refuse to accept your immediate answer, because I guarantee you, if you just zoom out, the answer to this question will be just as undeniable for you as it was for Concorde. Thanks a lot. I'll be hanging out in the Slack room afterwards if any of you want to chat with me. I'd love to talk. Thanks a lot for being here.
Well, very good, Nick. I'm sorry about that. Well, exceptional. Thank you so much all for joining us. Now, this is moving us into the very end of our 3 days together. So, with that being said, let us dive over again as the last and final reminder, at least from me, that is, don't forget to jump over to the Slack channel where Nick will be available to answer any questions you might have. And of course, enjoy the break and then into our closing keynote and our final close up of the 3 days. All right. Well, thank you so very much, everybody. It has been my pleasure, and I will see you soon.